Listening to the bell, the patient went to see a doctor and he said to the doctor, I keep thinking I'm a bell. The doctor wrote him a prescription and said, take this, if it doesn't work, give me a ring. Alright, problem of the day. If you make X items, the revenue is 50X, the cost is 0.001X cubed minus 0.1X squared plus 12X plus 1500. How many items should you make to maximize the profit? Basically, just get it set up so that you know what you're doing. Okay, let's just talk about it. How do you figure out profit? What is profit? Revenue minus cost. So that would be the setup. Then you take your revenue and you subtract the cost. Minus 0.01x cubed plus 0.1x squared minus 12x minus 1500. So I just took this minus that. And if you want to maximize the profit, what do?
Take the derivative.
Take the derivative. So then derivative would be 50 minus 0.003x squared plus 0.2x minus 12. So that's basically the setup. Then what do you do with that? Find where it equals 0. If you're allowed to use a calculator, you would simply put that function in on the calculator and see where it crossed the x-axis.
There's a part on the test where we don't use a calculator.
What's that?
Is there a part on the test where we don't use
The AP exam? Yeah, 1/2 of the exam.
What?
What half of that
What?
would that be? Well, this is news to me.
What do you mean news to you? I've told you that before.
No, you never told us that.
Really?
One.
Oh, yeah, I said.
I did not know.
There's a free response with calculator, a free response without, a multiple choice with calculator, multiple choice without.
No.
Oh,
Yeah.
wait, so did we put it all up
Huh?
or something? Or just
Yeah, it's split up into 4 parts.
Okay.
Does the AV test part have calculator?
Does it have really easy, simple math in it besides like calculus parts of it?
Okay, so, for example, this question would be with the calculator. They wouldn't expect you to solve that equation by hand. All right, so I figured out where it crossed, and it crosses 0 at it crosses at 150.7, so you'd have to make 151.
How do you know that?
Okay. What's that?
Wait, don't you have to figure out where it's increasing and decreasing those?
Okay, this function is coming down, and then so it's a derivative. The derivative is positive and then negative, which means the function is going up and going down, so it's a maximum right at that point. This is not a graph of the function, that's the graph of the derivative.
But if you didn't have it,
Then it wouldn't be that complicated.
Just put it out. Just get it out. Except for this well, okay, so I'm just well, you can just say like yeah.
Okay, physics people, help me out. What's work? Force times distance. Work is the force in the direction that you're going times the distance. Okay? Did you do Hooke's law in physics? Okay. Here's Hooke's law. If you take a spring and you pull the spring, it takes a force, and it takes more force the farther away you get because you're pulling on a spring that's really getting stretched out. So the distance that you hold the spring affects the force. And so the force is a constant times x. And the constant will change depending on how stiff the spring is. You have a stiffer spring, k is going to be a bigger number. So when you're doing a spring problem, you use Hooke's law. The force that the spring has depends on how much distance you have to pull it through. So let's do an example. A force of 10 newtons, and if you're not in physics, you don't know what newtons is, you don't have to worry, just the force of 10 is needed to stretch
we worry about you in the work family.
I know, M is used way too much for like 15 billion different.
All right. Let you copy it, and I'll explain it. A force of 10 newtons is needed to stretch a spring 2 meters. How much work is done if you're going to stretch it 4 meters?
If you were paying attention 5 minutes ago, you would know it was.
All right. Here's Here's a spring, and we're going to stretch the spring a distance of 4 meters. How much work is going to be done to stretch it 4 meters? All right. To figure out how much work is going to be done, we need the force. Now, the problem is, work is force times distance. So can you just go 4 meters times 10?
No.
No. Because what's happening to the force? It's changing as you pull it out. So what we need is to figure out the constant for this particular problem. So what's the force constant? Well, we know that the force of 10 newtons is needed to move it 2 meters. So K is equal to 5. All right? So the force for this spring is 5x. Now, what's happening? The work being done, I pull a little distance times the force. Then the next distance I pull it, I'm going to have to use more force. And then the next distance I move it, I'm going to have to use more force. And so I'm going to have to just keep adding all those little increments of work up. Well, what do we do when we add a bunch of increments up? We integrate. So the work done is going to be the integral that goes from 0 to 4, force times dx. Whatever force you need to pull a little distance, plus whatever force you need to pull a little more distance, plus what force you need to pull it the next distance. And so essentially you're just adding all of those little pieces of work up, which is an integral. So now what do we put in for f? 5x. So it's the integral 0 to 4, 5x dx. And the integral would be 5x squared over 2, evaluated at 4 and 0. Gives you what? Five times 16, which is 80. 80 divided by 2. The answer is 40 Newton meters. Physics people, what's 40 Newton meters?
Whoa. Oh yeah, she doesn't
Wait.
I know.
What'd you do it last September or what?
Maybe don't have
It's June.
You got it. I don't know why. No.
All right.
I took physics a year and a half ago. I don't
Okay, the point of that is when you figure out something such as work, force times distance, if the force doesn't change, you just multiply the force times distance, you're done. But if the force is changing throughout, then you have to integrate and figure out each individual step of the way as it changes. All right. Any questions on that? Okay, we'll get to a lot more use of that in section 7.5. But today we're going to 7.2.
It's really hard.
Let me know when you're back from the commercial.
All right, folks, time to pay attention.
All right. Catherine has discovered this is very easy. The lecture takes about 3 seconds. All right? We're trying to find the area occurs, well, we know how to find the area under F, and we know how to find the area under G. So to find the area from F to G, we would just subtract the results. So the area is the integral that goes from A to B, evaluate F minus G, and there's the lecture. Well, that's the fundamental part of the lecture. Now we'll do the examples.
All right.
Are the examples okay?
Are the examples what?
Are the examples also going to take 3 seconds?
No.
Okay, good stuff.
Mr. Kiefer,
Yeah.
why do you have that awkward space between, let's say, B? And then like the, between like that.
I'm getting old and I probably just was readily confused. We're Charles.
Mr. Kiefer, how did you feel about our
I'd like to go on to the
Okay. First example. Find the area between the curve y equals secant squared of x and y equals sine of x from 0 to pi over 4. All right. If you were to graph y equals secant squared of x, it's going to be a graph that goes up like that. And if you were to graph y equals the sine of x from 0 to pi over 4, it's going to be a graph that looks something like that. And so this is the graph y equals secant squared of x. This is the graph y equals sine of x. And you're asked to find the area between them. So it's very straightforward. Okay? Yes.
Oh, I think I just saw the answer because this you can just do secant x squared and that would be this, yeah. Okay.
So the area is the integral that goes from 0 to pi over 4. You simply take a function on top, secant squared, minus sine of x dx. 90% of the time when you're doing problems of this nature, it's going to be in the calculator section where you can just plug the thing in the calculator. But there are going to be times where it's going to be the non-calculator where they'll ask you to set it up. And so here we set it up, and they may even ask you to find the antiderivative, just don't plug in the numbers. So you still have to have the skills of doing antiderivatives. And both of these are pretty simple. What's the antiderivative of secant squared? What do we think the derivative of is secant squared? Tangent. So this is tangent of x. And the antiderivative of negative sine would be a positive cosine. And then we evaluate that at pi over 4 and 0. Okay, what's the tangent of pi over 4?
1.
Tangent of pi over 4 is 1, because pi over 4 is a 45-45 triangle, and so the tangent would be 1. What's the cosine of pi over 4? 1 over the square root of 2. And then minus, what's the tangent of 0? 0. And then minus the cosine of 0, which would be 1. So the final answer is square root of 2 over 2 or 1 over the square root of 2.
Should we be asked to do something like that, like finding the tangent of 45
should know that. I mean, but see, the thing is, I don't remember it, so I quickly just make a little triangle, and then I quickly know what it's going to be. So you either memorize them, or just remember in your brain to make a right triangle. Okay. You tired of the waiting pool now? Let's get out of the waiting pool. Okay. Look at this one. What's different about this one? Didn't give you any boundaries to go from. So, okay, let's take a look at the first one. What's that a picture of? Parabola that points down and has a y-intercept of 2. So that means we're going up here to 2, and it's a parabola that points down. What's this a picture of? Line that has a slope of -1, so it's going through here with a slope of -1. And so we're now trying to find the area enclosed by these two curves. So now what we need to come up with is what is this point and what is that point? Well, that's where the two graphs intersect or equal each other. So what we can do is set them equal to each other and solve. So 2 minus x squared equals -x. I'm going to bring everything over to the right side. And I get x squared minus x minus 2. No, I brought it all over to the right side.
Oh, okay, yeah.
So then I'd have a positive x squared, easier to factor. And so this is x and x. 2 and 1, minus and plus. So it looks like x equals 2 and x equals -1. And that looks pretty good by my picture. So we are now going to integrate from -1 to 2, because then this is the roof, that's the floor. Right? So the area equals -1 to 2. The function on top is this one. So that's the roof minus the floor, which would be minus a -x. Now, let's make sure we're okay with this area being down here. Because what happens when you integrate something that's underneath? It's a what? It's a negative answer. But what are we doing with it? We're subtracting it. And so what happens when you subtract a negative number? It makes it positive. So essentially we're adding this area on. Okay? Before when you found the integral of something like this, and you integrate it here and there, the total integral, this canceled that out. But that's because this was the roof here and now it's the floor. Here, this is the roof and the floor stays down there. So anything that, when you subtract something that's negative, you're simply subtracting the negative and it's basically adding it back so that you get the total area. Okay, so there's your integral. You can just use analytic methods and it works out pretty simple. Gives you an area of 9/2. Okay? So, the only thing different about that one was we had to find the endpoints that we were going to integrate. Other than that, it was still pretty easy. All right. y equals x minus 2. Find the area that is in only the first quadrant. Okay, what's this a picture? What's this a picture of? Okay, half a parabola. That's a picture of a... I thought you were here. It is bad. It is, which means you must really be talking loud. And that means you're talking so loud you're bothering them too. All right. Y equals x minus 2. Is a line, y-intercept of negative 2. Down to negative 2. And it goes up at 45 degrees. Okay? We're finding the area sandwiched in between square root of x and y equals x minus 2, but only in the first quadrant. So we're only trying to find that area. Because that's what was asked. Now, we have a problem because here we had a continuous roof and a continuous floor. One function defined the roof, one function defined the floor. Here we don't have that. We've got a continuous roof, and then we got a function defining the floor, but then here, that doesn't define the floor anymore. Something else is defining the floor.
Why?
Thrown in the column.
What? Well,
They're not intersecting together.
we're looking for the area only in the first quadrant. We're not looking for the area that's sandwiched in between the bottom curve and the top curve.
Then why do we look at 3 quadrants over there?
Because there was no restriction over here. That didn't say, just find the area that's in the first quadrant.
Okay.
All right, there's 2 or 3 different ways you can do it. So throw out an example, raise your hand and tell me what we should do. Christina.
Integrate from the axis to the point where x minus 2 crosses.
Okay, actually, I haven't driven it drawn it to scale, but it crosses at 1. And this crosses at 2. Because if I put a 2 in here, no, is that right? It crosses at 2. This is at 4. There we go. Okay, so say it again.
Integrating parts, so doing from like the y-axis to the point 2.
Okay, so we're going to integrate 0 to 2 of
Square root of x.
just this function here.
Yeah.
Square root of x. And then you're going to do what?
And then add the integral from like 2 on.
Right, 2 to 4. And the function on top, which would be the square root of x, minus the function that forms the floor. Very nice. Okay? Yes. Okay, let's make, yes, hang on. Everyone okay with that? That's one option of doing it.
Yeah.
Well, we won't rush, just make sure you understand. So what Christina said is just find the area in this little part here by integrating from 0 to 2 of just this. Then find the rest of the area by integrating from 2 to 4, taking the roof and subtracting. All right, what else could you do?
You can integrate the whole thing and subtract
Okay.
triangle.
You could also integrate the whole thing to the top, 0 to 4, which would then give you this whole thing. So we're not even, and then what? And then subtract the triangle that's created by that. Well, we don't even need to integrate. We can just subtract the triangle. 1/2, 2 times 2. Okay, any others?
Could you integrate by take the integral of the subtracting and then
Okay.
subtract the triangle underneath?
Yeah. You could integrate the roof here, which is the square root of x, minus the floor, which would give you the whole thing, and then subtract off the little triangle here, which is 1/2, 2 times 2 also. So those are three different options. Whichever one is easiest to do would be the one to choose. Okay.
Take care of the goodie.
Okay.
Oh, yeah. Someone makes Oh, yeah. Really sounded like I was worried. It's Freud. It's Freud.
Okay. All right, this is the same problem. Same problem. What was the issue in this one? The issue in this one was what? The roof was created by one function, but the floor was created by two, more than one function. So that causes problems. So what we're going to do is take a different look at it. Instead of looking at the floor to the, the roof to the floor, let's look at the right side of the house compared to the left side of the house. The right side of this house is determined by this line. What's the left side of the house determined by? The curvy function. There's no break. There's no break. One is, there's a definite side and a left side. As opposed to here, there was a roof, a floor, and a floor. We had to break it up. If we look sideways, just take the right wall and compare it to the left side. We don't have to break it up. We do have to change which direction we're going. Because remember, when you integrate, you're theoretically taking the length of the function and multiplying it by delta x. That's where the function and the dx come from. You can also find the area going in this direction. But now, what's the width of our rectangle? A delta y or a dy. So now everything has to be in terms of y. Okay? So this function here, which was originally y equals the square root of x, now we want x in terms of y, so x is y squared. This function right here was y equals x minus 2. In terms of x, it would be y plus 2. Okay? So now the area that we're looking for, instead of taking an integral that goes left to right, we're going to take an integral that goes from bottom up in terms of y. So we're going to start down here at 0. We're going to go as high up as the function, the wall goes. It's going to go up to a height of 2, because if we put a 4 in here, we're going to get a height of 2. And then what's the function? Well, we look for the wall on the right side. What's the function on the right side? Y plus 2. And then we subtract the wall that's on the left side, which is
Should it be 0 to 4 or 0 to 2?
0 to 2. Thank you. 0 to 2. Yes, we're going up here.
Switch the y and x.
And so this would be y plus 2 minus this wall, which is y squared.
So wait, just go like this.
Yeah, turn your head sideways.
I can see it now.
Okay?
Can we do this on a calculator?
This is dy. Okay. Yeah, you just remember when you integrate, it doesn't matter what you call a variable. You could call this t and t squared and dt, it's the same thing. Okay, so now, two things happened that were good. One is we didn't have to break it up. But what's the other thing that happened to turn out pretty nice? Look what you're integrating. What are you integrating? A just nice, neat polynomial. Very, very simple to integrate. What did you have to integrate over here? A square root. Square roots are a little bit tougher, especially if there's a big number inside the square root. So, the point is when you find the area, you want to choose the method that makes the integral the easiest, especially if you're doing it by hand. If you're not doing it by hand, it doesn't matter. Just plug in the calculator and get your answer. But notice in this case, not only did it just go from my one side to the other side, the integrand became a very simple integrand. And that would be huge if this square root over here had been the square root of some messy term. You know, if it had been that, it would have been a lot messier to integrate than just a polynomial. Okay? All right, I got one more to do. Can you make it?
No.
Yes.
I'm on the board. You get to elsewhere.
I'm slowly withdrawing my.
I know.